We're now ready for the final part of Chapter 9, and this is where we get to the culmination. Well, any algebra section or chapter is going to introduce new types of functions, but the ultimate goal of introducing new types of functions is to be able to do algebra with them, meaning solve for the missing piece, right? We need to solve equations that have exponentials or logarithms in them. Okay, so whenever the variable appears in an exponent, we need to figure out a way to solve for that variable. And that's going to turn out to be using logarithms to do so, and vice versa. We need to be able to solve whenever the variable is inside of a logarithm. And in order to do that, we're going to use some of the properties that logarithms have. So let's talk about how we solve those two different types of equations. Let's start with, of course, the obvious. What is an exponential equation? So an exponential equation is an equation containing a variable in the exponent. So using skills that we've developed in this chapter, we're now going to be able to solve those types of equations. So the first strategy, and this only works in some cases, but if it does work, it's definitely a shortcut. What I would suggest we do initially is solve by expressing each side as a power of the same base, and if the result looks like this, right? If you can write both sides as having the same base, and m and n may be, expressions involving x, maybe numbers, whatever, but you get something like this, b to something else, then you automatically know that their exponents have to be equal. Okay, let me demonstrate with this example right here. I have 5 to the 3x minus 6 and 125. Now, I've got that x trapped up in the exponent, and it's hard to get down, but I notice this has a base of 5, and I can write 125 as a power of 5. Right? In fact, 125 is the same thing as 5 cubed. Now this is where it gets hard, is you got to be able to recognize that numbers in there can be written as those powers, and in many cases they can't. In fact, in most cases this doesn't work, but in the case that it does, this makes it real simple, because now I've got 5 to the 3x minus 6 is equal to 5 to the third. So what does that say? That says 3x minus 6 has to equal 3. This exponent has to equal this exponent. If I add 6 to both sides now, I get 3x is equal to 9. Divide both sides by 3. That means that x is 3, and that's my solution. All right, but again, you have to recognize that you can write each side as that common base. Here's another one. Now, at first glance, you say, well, I can't do that because I can't write 32 as a power of 4. But I can actually write both 4 and 32 as a power of 2, right? 4 is 2 squared, right? Oh, hang on just a second. All right, let's try this again. 4 is 2 squared, right, raised to the x, and 32 is 2 to the fifth. 2 times itself 5 times. All right, well, 2 to the 2 to the x means 2 to the 2x. Remember, you multiply exponents. Now I can say that 2x must equal 5, right? Because if 2 to the 2x equals 2 to the 5, then 2x equals 5. Divide both sides by 2 to solve for x. I get 5 halves, right? All I'm doing is setting these exponents equal to each other to get that equation right there. And that gives me my final answer. Now what happens, in the off case, in fact, the more common case, that I had something like 5 to the 3x minus 6 equals 7. Problem there is I can't write 7 as a power of 5. I can't write 5 and 7 as the power of the same number. I've got to have another technique. So we have a more robust strategy, which we'll call strategy 2. Let's look at it. Strategy 2 uses natural logs to solve exponential equations. To begin with, the first step is to isolate the exponential expression. You're going to try to use some technique to get the variable out of the exponent. So get the exponential part by itself, move everything else to the other side, either by addition, subtraction, multiplication, or division as necessary. Then take the natural log of both sides. Now we're going to simplify using the properties of logs. And the most important property is that power rule that says if I had that variable up in the exponent, it pops out and lands in front, x natural log of b. So if b is just a number, then this part is just a number, and you've got your variable out of the exponent, and you can now solve it using earlier techniques. Now, on the other possibility that the actual logarithm, or sorry, the actual exponential that you're taking the log of is the same as the base. That is, if I take natural log of e to the x, remember that cancels each other out, and I don't have to worry about the natural log of e. Okay, and then solve, because by that point you've gotten rid of the exponential. It's now just a problem like we already know how to solve. Let's try this one. In this example, we have 5 to the x is equal to 134. To solve this, I could not write 134 as a power of 5, so I begin by getting the exponential part by itself, which it is. It's already there by itself. Now I'm going to take the natural log of both sides. Just put a natural log in front of the 5 to the x and in front of the 134. Now use the property called the power rule. It says I can take the x out front and have x times the natural log of 5 equals the natural log of 134. Okay, now how do I get the x by itself? Well, notice the x is multiplied times this log of 5. So divide log of 5 on both sides, natural log of 5 on both sides. So x is the natural log of 134 divided by the natural log of 5, which I plug into my calculator. Take 134 natural log divided by natural log of 5 gives me 3.04. Now in all of your homework it'll tell you how many decimal places to carry it out whenever you approximate this. Let's try this one. 7e to the 2x equals 63. Begin by getting the exponential by itself. Here's the exponential term. So I'm going to divide both sides by 7 and have e to the 2x is equal to 9. Taking the natural log of both sides leaves me with 2x equals the natural log of 9. Because natural log and e are the same base, they cancel. You're left with then dividing both sides by 2. X is the natural log of 9 divided by 2, which in my calculator is 1.099. Approximately. Now that we can solve all of our exponential problems, let's talk about logarithmic equations. So again, the obvious starting place is to talk about what we mean when we say a logarithmic equation, which kind of has an obvious definition. The logarithmic equation is an equation containing a variable inside of a logarithmic expression. In order to solve a logarithmic equation, we begin by simplifying each side. And remember, with logarithms, that can mean two different things. It can mean expand the logarithms, but in this case, we're going to talk about combining the logs. Because if we can get it as log base whatever of something equals something else, then we can use the definition of the logarithm, right? Use this little spiral rule. So if you have log base b of x equals y, remember that's the same thing as b to the y is equal to x. Once you do this, if the logarithm had the variable inside, right, the variable's right here, then that variable is going to be right there. Which means we've gotten the variable out of the logarithm, so we can solve. Now we check for solutions that may be extraneous. Okay, and the thing you've got to check for is if negative or zero values occur inside of the logarithm, because remember, you can't take the logarithm of a negative number or of zero. Let's go through an example. In this case, we already have the logarithm by itself on one side. It's completely simplified, meaning that there is only one log. Then in order to solve this, I'm just going to use the definition. Right? I'm going to do 2 to the third is equal to what's inside. Now 2 to the third equals x minus 4. Go ahead and calculate 2 to the third. That turns out to be 8. So to solve for x, I'm going to add 4 to both sides. That says x is 12. Now we got to check. Log base 2 of 12 minus 4, is that equal to 3? Log base 2 of 8 is 3. That checks. Really what I'm checking for is what happens inside here. Is this, if that's positive, it's okay. If it's negative or zero, it's not okay. Example B. We have log base B plus log, sorry, not log base B, log of x plus log of x minus 3, all has to equal 1. Now, in order to simplify this, I first combine the logarithms. So using the fact that the product rule says the sum of two logs becomes the product of their insides. So I can rewrite the equation as such. Now, what's the understood base? The understood base, since there is not one, is 10. So my equation, by definition of logarithms, looks like this. 10 to the first is equal to x times x minus 3. Or 10 is equal to x squared minus 3x. This is now a quadratic equation. To solve the quadratic equation, I need to get it equal to 0. So I'll subtract 10 from both sides and have that x squared minus 3x minus 10 is equal to 0. Now, I believe factoring works on this one, which is always the best technique to use whenever you can with quadratic equations. X plus minus, I think, 2 and 5 work here. All right? That gives me negative 10. Negative 5x plus 2x is negative 3x, so that checks. Now, setting each one equal to 0, x plus 2 equals 0, and x minus 5 equals 0 gives me x is equal to negative 2, and x is equal to 5. Now I can automatically rule out x is equal to negative 2, and well, the reason is because I can't plug in a negative inside here, right? That's extraneous. Which leaves us this. Alright, how about this one? 4 times a natural log of 3x is equal to 8. I'm going to divide both sides by 4 to get the logarithm by itself in this case. So I have natural log of 3x is equal to 2. Again, the definition of the logarithm says I'm going to do the base ratio of the side equals what's inside. Remember, the base on this one is understood to be 2. So I end up with 3x is equal to e squared. E squared equals 3x. Dividing both sides by 3, x is equal to e squared over 3, which, plugging that in, does not give me any negatives or zeros inside because e is a positive number, so e squared is a positive number, so everything's fine, and that will check. Let's look at a couple of applications in practice where we might run into formulas that involve exponential or logarithmic equations, and then we're given enough information, we have enough information to solve for some missing piece, right? So here's an example. Medical research indicates that the risk of having a car accident increases exponentially as the concentration of alcohol in the blood increases. The risk is modeled by R equals 6e to the 12.77x, where x is the blood alcohol concentration, and R, given as a percent, is the risk of having a car accident. At what blood concentration would a 17% risk of a car accident correspond to? So, looking at the model, and reading this a couple times too to make sure we completely understand, we identify that X being the blood alcohol concentration, that's what we're trying to find. There's our unknown piece. But what we do know is R, right? And R, given as a percent, means I'm going to plug in 17 for R and try to solve this for X. Now, our shortcut method is not going to work here because it's very hard to try to figure out whether or not a number is some power of e, so I suggest we use our logarithm trick. What we're going to do is we're going to get the exponential by itself, so divide both sides by 6. 17 divided by 6 is 2.8333. I recommend going several decimal places anytime you're working with logarithms for accuracy's sake. Now I'm going to take the natural log of both sides. Natural log of e to the 12.77x. Okay, remember over here this is going to cancel out. I take the natural log of this, I get 1.40145 is equal to 12.77x. If I divide both sides by 12.77, I get a blood alcohol concentration of X is equal to 0.08. Okay, if your blood alcohol concentration is 0.08, that corresponds to a 17% risk of a car accident. Okay, 0.8 blood alcohol concentration. Let's do another one. This problem goes back to our compound interest formula. The formula A equals P times 1 plus R over N to the NT describes accumulated value A of a sum of money, the P, the principal, after T years at an annual percentage rate R in decimal form, not percent form, but decimal form, compounded N times a year. So how long will it take $25,000 to grow to $500,000 at 9% annual interest compounded monthly? Now, if you're asked how long, what variable are you hunting for? Well, clearly you're hunting for T. We're trying to find the unknown T. So what do we know? We know how much we start with, so that's the principal. We know how much we want to end up with, that's the annual amount. Here's our percentage rate. Remember, we're going to plug it in as a decimal. And compounded monthly means N is equal to 12. So we plug in everything we know. The only unknown then at that point is going to be T. Plugging it in, we end up with 500,000 equals 25,000. 1 plus 0.09 divided by 12 raised to the 12t. First thing we want to do is simplify inside the parentheses. So that would be 500,000 equals 25,000. 1 plus 0.09 divided by 12 is 0.074. 0.0075 raised to the 12t, which I could go ahead and combine that in one step. Now let's go ahead and write that all together as 1.0075. Now we want to get the exponential expression by itself, so I divide both sides by 25,000. 500 divided by 25, or you can do the whole thing in your calculator. It gives me 20. 20 equals 1.0075 to the 12t. Now we take the natural log of both sides. Using the fact that I've got the power rule, I can bring the 12t out front. I'll have 12t times the natural log of 1.0075 is equal to natural log of 20. To get the t by itself, recognize the t is multiplied on both sides by this thing. So I can divide off everything except the t. 12 natural log of 1.0075 on both sides would leave me with t is equal to the natural log of 20 divided by 12 natural log of 1.0075. Give me the number of years. And I'm going to go to my calculator. Natural log of 20 divided by 12 divided by natural log of 1.0075 gives me 33.4 years. Okay? Or more accurately, if I take the 0.4 times 12, that gives me the number of months. So 33 years, and 0.4 of 12 is 4.8, so 5 months would be required. Last example is an application problem that involves a logarithmic function that's modeling something, and we're going to use it to find that missing piece, that unknown piece of information. We have a function f of x is equal to 34.1 natural log of x plus 117.7. This models the number of U.S. Internet users, f of x, in millions, x years after 1999. And by which year would we expect 200 million Internet users according to this model? All right, well, we're going to plug in 200 then for the number of millions of Internet users in the U.S. So we plug it in for f of x. 200 needs to equal 34.1 times the natural log of x plus 117.7. So we're trying to solve for x. To do that, let's begin by getting the natural log expression by itself. First, I need to subtract off 117.7 from both sides, leaving me with 82.3. That equals 34.1 natural log of x. Divide off the 34.1 from both sides. So 82.3 divided by 34.1 is 1.2893 equals the natural log of x. Now we use the definition of the logarithm in order to get the next step. Remember, there's an understood e here, so it's e to the 1.28393 is equal to x. And I just got to plug that into my calculator, and I get 3.6. I did something incorrect here. My division was off. Alright, now I could easily go back and correct this with the video clip, but I want you to see that sometimes we make mistakes and we got to fix it, right? You've made mistakes on your homework, I'm sure, and you had to go back and fix the mistakes we've made. Here I've got an error somewhere, and I recognized it because this seemed a tad soon for millions of Internet users. Here's the mistake. If I double check this in my calculator, 82.3 divided by 34.1, I get not this, so this is wrong. I get 2.41349, right? And you may have got that if you were doing this on your own in your calculator. Now again we do the same step, and let's check again. We end up with e to the 2.41349 is equal to x. Plugging that in, taking e to that power, I end up with x is equal to 11.1. Now interpret your result. 11.1 would mean 11.1 years after 1999. So 1999 plus 11 is equal to 2010. All right, that's the end of section 9.5, and in fact, that's the end of chapter 9. We have covered all we're going to cover about exponentials and logarithmic functions. We're now to the point that we can solve equations and actually solve some real-world problems that involve those types of functions. All right, so that's the end of chapter 9.